When we multiply with exponents, we want to write our answers, our product, as an exponent. We're not going to expand this out and write it as a standard number. We don't need to multiply all these numbers in a calculator, but we do want to apply exponent rules. And here is an example of what's going on. I'm going to write the first one out for you. 4 to the second power really stands for 4 times 4, and then 4 to the third power really stands for 4 times 4 times 4. And you can see that if I were to multiply those together, that I have 5 4s sitting here. There's 2 from this one, 3 from that one, and if I put it back as a power, I can just write it as 4 to the 5th. And really what I want you to see is that we can take these exponents here when we're multiplying. As long as the bases are the same, these powers can be added. So here's an example. I have 2 bases that are a 5, and so we're going to take those 2 exponents and we're going to add them up. It's going to be 2 plus 3 as an exponent, which is just 5 to the 5th power. And that's how we want to write our answer using exponent rules. So the third problem here, we have a base of a 2, a base of a 2, and another base of a 2. We don't usually write ones, but on this one example, I give you the 1. We're going to take all these numbers here and we're going to add them up, and 3 and 7 make 10, plus 1 is 11. So that's just 2 to the 11th power. We don't need to multiply 11 2s. We're okay with that. This right here, I can see it's in expanded form. Count the 6s. We have 5 6s. That means 6 to the 5th power. We don't need to multiply that. Here you can see I have 3 2s, and here's 2 more 2s for a grand total of 5 2s. So the base is a 2 and the power is a 5. Here's an example where we didn't write the power, but that power right there on the 8 really is a 1, and 1 plus 7 plus 2 is 10. So the answer is 8 to the 10th. So when we divide and we're going to apply exponent rules, if the bases are the same, here we see both the bases are a 4, then we can subtract the exponents. If I were to expand out the first problem, the denominator would only have 2 4s. The numerator that I'm writing here has 6 4s, because that's 4 to the 6th power. And on the bottom here, let's go ahead and put our 2 4s. And if I were to reduce this, every 4 on the bottom would cancel 1 out on the top, and then I'm out of 4s down here, and what I'm left with is 4 of them up in the numerator, and we're going to get 4 to the 4th as an answer. I could have looked at this and come up with that answer by simply taking these 2 exponents and subtracting them. It's always going to be the top one minus the bottom one. It's 6 take away 2 in this case, so our final answer for this will be 4 to the 4th. Over here we can see they both have a 2, so we're going to write it as a subtraction problem, top one minus the bottom one. That's going to leave me with 3 of them, so it'll be 2 to the 3rd power. And that would be our answer in applying our exponent rules. Now this 5 to the 2 over 5 to the 5th would be 5 to the 2 minus 5, and 2 take away 5 is a negative 3. So as an exponent, we would write it as 5 to the negative 3rd. We don't usually want to leave negative exponents in our answer, so we're going to write this, if you recall from the last video and from the first part of 2.1, that negative exponents just mean division, and if I move it to the bottom, its exponent can become positive. Now 5 to the 3rd power is 5 times 5 times 5, which is 125, so this right here is a good enough answer for these right now. If you had to expand it out, it would be 1 over 125. In this problem here, we've got a little order of operations. We're going to deal with the numerator all together first. Before we divide, I notice right away that this doesn't have an exponent, so I'm going to give it a 1. 5 to the 3rd and 5 to the 2nd, we just add those up, it becomes 5 to the 5th. That's just multiply rules, but I still have to divide by that 5 to the 1st power. And 5 take away 1 is 4, so my final answer on this will be 5 to the 4th power. Here, 10 to the 3rd over 10 to the 5th, again, I'm going to subtract these exponents, top one minus the bottom one, 3 take away 5, which is 10 to the negative 2 power. And whenever I have negative exponents, we don't want to leave it that way. I'm going to go ahead and put it on the bottom, I'm going to put it in the denominator, and it's going to change that to be positive. And that's going to be good enough for me for right now. 4 to the 4 over 4, as you guessed, this is a 1, and I'm going to put it there just so we can see the subtraction. And 4 take away 1 is 3. So my final answer on that problem, 4 to the third power. So let's take a look at another rule of exponents, which is the power of a product. And power of a product, we're going to see some parentheses, we're going to see some numbers on the inside, and each number on the inside is going to become a base. And the power is going to apply to every number that's inside the parentheses. So let's go take a look at an example of what this looks like. You can see the first problem there. We have 3 times 4 on the inside of parentheses, and it's being raised to the power of 2. And the 2 applies to each of those. So the 3 becomes its own base, and the 4 also becomes its own base. So this is one way that we can write this as a power of a product. Now, if we wanted to simplify this further, 3 times 3 is 9, and 4 times 4 is 16. So we could write this as 9 times 16. And if we were asked to simplify it, that means we want to multiply that all together. You would get 144. Now, there is another way to look at this, and that is sometimes we might want to multiply the numbers in the parentheses first. Order of operations would say that that's okay to do. So we could call this 11 to the second power times 2 to the second power. And on some tests, they may want it written out as an exponent, and this would be acceptable. We could also take the numbers on the inside and multiply them together, 11 and 2, and get 22 raised to the second power. And so either one of those, if we're writing it in exponents, either one of these could be acceptable. Now, we're not going to get too bogged down in an explanation about the power of a power rule, but it'll be acceptable to just understand that if we raise a power to the power, that the exponents are going to get multiplied. So 4 to the second raised, this really reads 4 to the second to the third. Or we have a base of 4, we have a power on the inside of a 2, and then a power on the outside. And these two exponents here are going to get multiplied, and 2 times 3 is 6. And so if I simplify it using an exponent rule, that's just going to be 4 to the 6th power. This right here is, I can see that I have a power of a 4 and a 2. With a base of a 2, the base stays the same. The base is never going to change. And 2 times 4 is 8. So 2 to the 4 squared really just means 2 to the 8. 5 to the second raised to the 8th power is just 5 to the 16th. Again, we're just taking the two exponents there and we're just multiplying them together. 6 to the 4 squared becomes 6 to the 8th. And 4 to the negative 2 to the second, we do have to apply some integer rules here. Negative 2 times 2 is 4 to the negative 4, but you're not going to leave it that way because you guys understand now that negative exponents aren't our friend. We don't leave that in a simplified expression. We're going to move it down to the denominator, and then it's going to become a positive exponent. So it's going to be 1 over, and then the 4 is going to come down to the bottom, and then it'll be a 4 to the 4th power. Now, if we need to expand that out and call that whatever it's going to be worth, we can. But usually it's enough to write this with an exponent rule. So 3 to the negative 2 raised to the 4 becomes 3 to the negative 8, but we're not going to leave it that way. We'll just call it 1 over 3 to the 8. Now, again, when we have a power of a product and each of these products has its own exponent, the 3 is going to multiply each of these powers. Now, notice that the 4 and the 2 are different bases, so we can't really apply anything special to these except to multiply them out in a calculator and figure out what it's going to be worth. But each of these exponents is going to get multiplied by that 3. So 4 becomes 2 times 3, which is a 6, and 2 to the 2 times 3, which is 2 to the 6. And that could be enough, and that'll be all right for us. We can also, when the exponents are the same, we can take these two bases and multiply them. It only works if the exponents are the same. So you could call this 4 times 2, which is 8 to the 2nd power. That could be raised to the 3rd, and that would also be 8 to the 6th. But again, that really only works when the exponents are the same. Can we take the two bases and multiply them? On this problem here, you got a negative times a negative. That's going to be a positive. That's going to give you 10 to the 6th. That'll be pretty easy to expand out. If I wanted to, it'd be a 1 with 6 zeros. That'd be worth 1,000,000. And this one over here, 6, and then 2 times negative 1 is a negative 2, but we're not going to leave it with a negative exponent. We'll write it as 1 over 6 squared. Now, after we complete these couple of examples, you should be okay to finish all the rest of the problems in the lesson. Let's take a look at example A. We're going to apply a whole slew of rules here. And the first one I notice is inside the parentheses, I have something I can simplify. Just like over here, I have something that I can simplify. 5 take away 2 is, I'm going to rewrite this and show my steps. That's 3 to the 5th. I notice now that I have times 3 to the negative 8. And right away I recognize that these two bases are the same, so I'm going to be able to apply an exponent rule there. Plus, and then 5 plus 2 is 7 to the 0 power. I see a 0 power. I know right away that that's worth 1. And I can take both of these exponents here with the bases being the same. I'm going to add the powers because there's my multiply. And 5 plus a negative 8 is negative 3. And that becomes 3 to the negative 3rd power plus 1. And 3 to the negative 3rd power, I'm not going to leave it as a negative power. We're going to move it to the denominator. It's 1 over 3 to the 3rd, still plus the 1. And 3 to the 3rd is 27. So this is 1 over 27. That's just a fraction. Not a big deal. Nothing to be scared about. And when I take 1 over 27, that's 1/27 plus 1. My final answer is just going to be 1 and 1/27, and that's all it takes. Let's go take a look at example 2. I've got 3 plus 1. I recognize right away that that's going to be a 4, and then 7 take away 3 is also a 4. So at some point, I'm going to be able to apply exponent rules because my bases will be the same. So let's take a second and rewrite the top of this. 3 plus 1 becomes 4. I'll put it back in the parentheses that were there. To the 2 to the 3. So I'll put a 2 here, and I'll put a bracket around it, and I'll put a 3 there. 7 take away 3 is 4. 4 to the 2nd power. I don't really need the parentheses, but I'll put them there just for the fun of it. And I now have a power to the power rule, so I'm going to apply the power to the power rule, multiply that. That becomes 4 to the 6th, because we multiply over 4 to the 2nd, and now because I have the same base, I can apply the division rule, which says when the bases are the same, the exponents can be subtracted. So my final answer is 4 to the 6 take away 2 power, which is 4 to the 4th. And that's it. Now you can go ahead and complete the rest of the problems on the lesson, and good luck.